Sure.
Okay, so what initially drew you to the field of planetary defense and asteroid deflection?
Sure. So to start off, my name is Brent Barbee. I'm a aerospace engineer at the NASA Goddard Space Flight Center, and then in addition to that, I'm a adjunct professor at the University of Maryland. So that's just a little bit about my background. So I was initially interested in planetary defense and asteroid deflection because I grew up during the 1980s, which was the time period when scientists were first understanding that a large impact about 66 million years ago by an asteroid or comet is what made the dinosaurs and 75% of everything else that was alive at the time go extinct. And so, when I was young, growing up and learning about this sort of as it was being introduced to the scientific community, my reaction was, well, not on my watch, right?
Yeah.
So I think we can do something about that. And so that was why it originally captured my imagination.
Yeah, okay. But was there like a specific mission or event that inspired you or yeah.
Well, yeah. So I mean, the specific event that I think would be most relevant would be the 1994 impact on Jupiter by comet Shoemaker-Levy 9, which was actually torn into 20 some fragments by Jupiter's gravity, and then all those fragments hit one after another and made these really impressive scars in Jupiter's atmosphere, and it was observed by the Hubble Space Telescope. So we got a pretty good view of that impact event. It was very striking, and captured a lot of people's attention, including mine.
Okay. Okay, that's awesome. So let's talk about some asteroid threats and detection. So since you're an aerospace engineer, how do scientists determine which near-Earth objects like NEOs pose a potential threat to Earth?
So there's a worldwide network of telescopes operated by astronomers who search for and track asteroids after they're discovered. And the observations of those asteroids are all uh, passed through the Minor Planet Center, which is a clearinghouse for all the observations made by telescopes of asteroids. And then those data are then sent through to the Center for Near Earth Object Studies at JPL. And there they have a system, an automated computer system called Sentry. And Sentry automatically calculates the probability of Earth impact for all of the known near Earth asteroids. And then if any of the asteroids seem to have a non-zero probability of Earth impact, then that gets flagged so that those objects can be examined further.
Okay, that makes sense. But how far in advance are we able to like predict an asteroid's path?
Yeah, good question. So let's see. When we discover the asteroids prior to the dates when they would closely encounter the Earth varies a lot. It depends on what kind of orbit the asteroid is in around the sun. It depends on how big the asteroid is. Those factors determine how easy or difficult it is for telescopes to see the asteroid. And so some real life examples are there was an asteroid named 2012 DA14 that was discovered in February of 2012. And, within, a month or so after that, we knew from processing the tracking data for that asteroid from the telescopes, we knew that that asteroid was going to come back around and make a very close approach to Earth exactly 1 year later in February of 2013.
Okay, so that's awesome. But are there like challenges? So like what are the biggest challenges in detecting and like tracking these like hazardous asteroids?
Yeah, so um, so some of the big challenges are that ground-based telescopes can only see in our night sky,
Hmm.
in the opposite direction of the sun. And so the other challenge is that asteroids don't necessarily have very shiny surfaces, so they don't reflect a lot of sunlight. And those two things make them challenging to detect and so therefore challenging to discover and track. So the solution to those problems is NASA's NEO Surveyor telescope, which is going to be launched in late 2027, according to the current schedule. And the NEO Surveyor telescope is going to operate at the Sun Earth L1 Lagrangian point, which is an equilibrium point about 1.5 million kilometers away from the Earth in the direction of the Sun. And it'll occupy what's called a halo orbit around that special equilibrium point. And then it has, instead of visible band detectors hooked up to it, it's got infrared detectors. So it's a roughly half-meter diameter telescope. So as telescopes go, that's not exactly gigantic. It's not as big as the Hubble by any means. But because of the fact that its detectors use infrared wavelengths, it's able to detect the asteroids more easily because the asteroids are very bright in the infrared. And that's why the NEO Surveyor telescope was designed that way. So that's going to
Okay.
help us detect more asteroids over time than what we're currently able to do.
Yeah. So on top of that, are there ever like blind spots where like asteroids could go undetected or like we just completely miss it or like miss see it? Is that often or?
It's not super often. Asteroids, for example, that might be on very Earth-like orbits, meaning that the asteroid's orbit around the sun is kind of similar to the Earth's orbit, so it's
Mhm.
kind of going around the sun at a similar speed. If an asteroid like that, if it happens to be hanging out kind of on the other side of the sun from us, then it would be very difficult to spot an asteroid like that.
Okay.
So
Yeah. So okay. On that note, let's discuss like some asteroid deflection, like the strategies behind it. So what are like the most promising asteroid deflection methods that are currently studied and used in practice?
So the only one that's ever been used in practice is called the kinetic impactor technique.
Okay.
So we launched a mission called DART,
Hmm.
which stands for the Double Asteroid Redirect Test. We launched that in November of 2021, and it collided with the smaller member of a binary asteroid named Didymos in late September of 2022. And the goal of the DART mission was to make a change in the orbit of the smaller secondary member around the primary member of that binary asteroid system. So Didymos is about a 780-meter wide asteroid, and then its secondary body, you can think of it as like a moon for the asteroid. For the main asteroid, is called Dimorphos, and it's about 150 meters in size. So DART targeted Dimorphos, and actually you can see an image of Dimorphos behind me.
Hmm.
So the asteroid right behind me, that is what Dimorphos actually looks like from DART's cameras as it made the final plunge to impact the asteroid. So it did indeed make a significant change in the orbit of Dimorphos within the ranges of what we had predicted. And so it was a very good first test of the kinetic impactor technique. And essentially, kinetic impactor just collides with the asteroid, transfers momentum, kicks off some ejecta from the asteroid that amplifies the momentum
Hmm.
change in the asteroid, and then that results in the asteroid's trajectory being shifted,
Okay.
essentially slowing it down or speeding it up, so that it misses the Earth later. Um,
Okay. Yeah.
the other techniques that we're studying are uh, the use of nuclear explosive devices. So, detonating a nuclear device near an asteroid will vaporize a thin layer of the asteroid's surface material that will then blow off the asteroid and give the asteroid a strong push in the opposite direction. So, we're studying that technique as well. And we're also studying a technique called ion beam deflection. So some spacecraft, like NASA's Psyche mission, which is flying out to the main belt asteroid Psyche, uses a type of propulsion system called an ion thruster. And so the idea behind ion beam deflection is you position a spacecraft like that close to the asteroid with a paired set of thrusters, in opposite directions so that it can fire them simultaneously to station keep near the asteroid. And one set of thrusters is firing at the asteroid.
Mm.
So it's a gradual technique. It takes time for the effect to accumulate, but if you do it for long enough time over the course of years, it'll gradually push the asteroid off course.
Oh, okay. So that's awesome. So in your experience, how do engineers like decide which deflection technique to use on a particular asteroid that they detect?
Yeah, good question. So what we do is we gather information about the asteroid's orbit. We gather information about what we think the asteroid's physical properties are, like its total mass, its density, and its shape, and things like that. And then we do what are called trade studies. So
Mm.
what we'll do is we'll set up simulations that simulate, what we think the kinetic impactor could do to the asteroid, what we think the nuclear device could do to the asteroid, what we think the ion beam system could do to the asteroid. And then we generate the performance results for each of the sets of systems, including the dates by which we'd have to launch them and all these kinds of things. And then we do a multivariate analysis where we look at things like launch date, what kind of launch vehicles would we have to use, how many spacecraft would we need, how quickly would the deflection be completed.
Mhm.
And we lay out all these factors that we care about, and then we compare the methods to each other according to each of those different factors that we care about, and then we see which missions seem to perform the best.
Okay, so now that's awesome. So now can we talk about we're gonna talk about some real world missions and research. So going back to the DART mission, could you discuss like the significance of it and specifically what we've learned from it since it was one of the main missions that we've done?
Sure. So the DART mission demonstrated several important things. So first of all, prior to the DART mission, the only high-speed intercept of an asteroid that we had performed was actually a high-speed intercept of a comet. And the name of the
Mm.
comet was Temple 1, and the mission was called the Deep Impact Mission. It was a science mission that launched in January of 2005, and it delivered an impactor to collide with comet Temple 1 in July of 2005, about 6 months after launch. And the impactor was a smaller subspacecraft that separated from the main spacecraft. So the main spacecraft was able to fly by and watch as the impactor hit the comet. So it hit the comet at a little over 10 kilometers per second, and the comet was roughly 5,000 meters wide.
Okay.
So that was really our only experience doing that. Then we have to compare that to what we expect to come up against within the asteroid population. So asteroids much smaller than 5,000 meters can do a lot of damage on the ground, and the asteroid population size frequency distribution follows a power law. What that means is that there are exponentially more smaller asteroids than there are bigger asteroids, which is a good thing for us because that helps keep us safe from large impacts. And what it means is that smaller asteroids that are big enough to still do a lot of damage to the ground, even if they couldn't do anything like what took out the dinosaurs, but they could still cause a lot of local damage, a lot of regional damage. So these are asteroids that are maybe 50 meters, 100 meters, 150 meters, 200 meters. That size range of asteroid, there's a whole bunch of those that we haven't discovered yet. And they could potentially do a lot of damage on the ground, so we'd want to be able to stop them. But they're smaller targets, right? I've said that comet was 5,000 meters. So now imagine you're coming in and trying to hit something a lot smaller than that. It's a much harder problem. So the asteroid that's behind me there, Dimorphos, that DART hit, like I said before, it's about 150 meters wide. So that was one of the challenges for the DART mission was, can you hit a smaller target going really fast?
Yeah.
And the speed that we were going at was a little bit slower than deep impact. We came in at about 6 kilometers per second,
Okay.
which is still really fast. That's still like 14,000 some miles per hour relative to the asteroid. So DART demonstrated the ability to perform what we call a hypervelocity impact on a smaller size asteroid that's in that size range of things that are still big enough to cause ground damage, but are small enough that they're difficult to target. So that was one of DART's big achievements. And so from doing that, we learned how to do that. Then the other thing we learned is, and this is one of the big questions we want to investigate with DART, remember I said that a kinetic impactor, it has its own momentum, it hits the asteroid and transfers its momentum to the asteroid, but then the kinetic energy of the impact kicks off a bunch of ejecta out of
Yep.
the crater on the asteroid. And that ejecta has momentum of its own.
Mhm.
And by coming away from the asteroid, it further changes the asteroid's momentum. Now, the thing is, you know, it's very difficult to predict how much extra momentum is going to be carried away by that ejecta. And we call that amount of momentum the momentum enhancement factor. So one of the big things we wanted to measure with DART was what's the momentum enhancement factor for the kinetic impact. Now, we'll have to do more of these missions because not all asteroids behave the same. So it's not like the momentum enhancement factor that we saw with DART is the exact same value that we would expect to happen for any asteroid for any type of spacecraft impact. But it does give us our first real data point. So going into the DART mission, we had this idea that the momentum enhancement factor was going to be somewhere in the range of, maybe between 1 and 2, or maybe up to somewhere between 5 and 6. That was kind of what we thought the bounds were. Now, in the DART mission, we didn't have a separate observer spacecraft that was already on station at the asteroid to sort of characterize it and measure the mass of the asteroid. So we actually don't know the exact mass of Dimorphos, which is the asteroid that we
Mhm.
hit. So we had to make an estimate for the ranges of mass values that it might have, and then generate our results for the momentum enhancement factor across that range of possible asteroid masses. And when we did that, what we found is that the range of momentum enhancement factor values, depending on what the actual mass of the asteroid is, was right within the range we predicted, kind of between about 2 and 5, roughly speaking. And the nominal value, or the average value that we calculated, was kind of right in the middle of that distribution. It was about 3.6. So what that means is that the the uh, the ejecta that got kicked off the asteroid had about 3.6 times the momentum of the spacecraft itself.
Wow. Okay. So that's great. So, okay, besides DART though, like, are there any upcoming or future missions that are focused on planetary defense that is truly exciting to you, or what do you think?
Yeah, I'm really excited about the INEO Surveyor mission, which is the telescope mission that I told you about. So
Yep.
there's currently something like, on the order of 10,000 some asteroids out there that are between the sizes of about 140 meters and 1,000 meters that we haven't found yet. And the INEO Surveyor telescope is going to be our very best tool to discover and then track all of those asteroids that we haven't found yet. It's predicted to be capable of doing a very good job of that. It's going to give us a lot better picture of what's out there, and hopefully give us a lot more warning time. So when it discovers an asteroid that's going to hit us in the future, hopefully it'll be able to catch it a lot further in advance, which is really important because the more warning time we have, the easier it is for us to do something about the asteroid.
Okay, okay, that's perfect. So now let's move on to some more like engineering challenges and innovations. And I wanted to get your thoughts, but what are like the biggest technical difficulties or challenges when designing an asteroid deflection mission, based on your experience?
So one of the current current research frontiers is understanding the process of asteroid fragmentation.
Mhm.
So one of the things that we have to think about when we're designing these missions is how much push do we have to give the asteroid to make it miss the Earth later? And that depends on a number of factors. It depends on where exactly on the Earth is the asteroid hitting. Because if it's hitting closer to the edge, then we don't have to push it much to get it off the Earth. If it's hitting more in the middle, then we have to push it a lot to get it off the Earth. Um, and it also depends on how much warning time we have. So, if we don't discover the asteroid until later in the game, then we might have to hit it a lot harder to get it off the Earth. Whereas if we had discovered it a lot earlier, we wouldn't have necessarily had to hit it as hard. So, depending on how hard we have to hit it, we have to then assess, is the asteroid going to stay intact? because if we hit the asteroid too hard, we it might start to break up. And
Mhm.
so then we have to figure out, well, okay, do we expect that a breakup might happen? And if it were to happen, what can we say about where the fragmented asteroid material would go? And so, is it a situation where there's some unpredictable effects and there could be some asteroid material left over that's still headed towards the Earth? Or would we be able to design it in such a way that all the asteroid material gets pushed away from the Earth, even if it's broken up?
Mhm.
And then on the flip side, we ask ourselves, how can we design the mission to break the asteroid up very forcefully on purpose so that
Mhm.
the goal of the mission shifts from being to deflect the asteroid as an intact single object and shifts from that to being, okay, let's break the asteroid up really hard and scatter the pieces really widely, so that the pieces are all small and the vast majority of them, steer clear of the Earth and maybe even steer clear of the Earth Moon system if we can manage it. So that's called a deliberate, robust disruption. And so that's really what we're trying to understand is how do we incorporate our uncertainties about about how the asteroid will respond to us pushing it into our design so that we can make mission designs that are cleverly able to handle those uncertainties, and then also figure out what other kinds of experiments should we do in space on asteroids so that we improve our understanding and reduce our uncertainties in how the asteroids respond to us trying to push them.
Okay, that's great. So asteroid deflection missions have multiple different steps, but what is like the hardest part? Because you have like detecting, you have like targeting, and you have like actual impact with the asteroid. But and some missions even have more. So like, what's like the hardest part? Like, because there's a lot of planning involved to it. So what's like the hardest
Mm-hmm.
specific part of it?
I would say there are several things I would say are very challenging. The first is to be sure that you initially detect the asteroid very far in advance of when it would hit the Earth, because you want to give yourself that really long warning time. And guaranteeing the ability to do that is difficult. And again, the INEO surveyor telescope will improve our ability to meet that challenge. The other thing that's challenging is, as you mentioned, doing the targeting and the guidance to hit the asteroid accurately when you're coming in really fast. That was one of the challenges that DART had to solve, and it solved it well. But nevertheless, for other asteroid missions, we might have to hit even smaller asteroids, or we might have to be hitting the asteroid going faster. And so that high speed intercept is going to remain challenging. That's for sure. Um, I would say those are probably two of the biggest technical challenges.
Okay. Yes. So, yeah, targeting is pretty hard, but so that requires a lot of precision. So, how do you like ensure precision is extremely accurate to the precise and whenever you're targeting like an asteroid that's millions of miles away, like how do you ensure it's super precise?
Yeah. So for that, you need to have a really good camera system on the spacecraft. So on DART, we had a camera called Draco, and Draco allowed us to see the Didymos system a little over a month before we were right on top of it. So that gave us, a good amount of time to do all the planning on the ground for the terminal guidance sequence, and then so that way the spacecraft was in a really good position to hand over control to the onboard autonomous system shortly before the impact. So, so having a good camera system on board that is powerful enough to see the asteroid, before you're right on top of it, you got to be able to see the asteroid a ways out to give the guidance system time to react.
Okay. So, how much of like a margin of error do engineers have, or would you say they have like almost zero? They have to be exactly perfect. How much would you say?
It varies from situation to situation. So DART was a demonstration mission, and which means that in some ways we had slightly larger margins to work with than we might have had on a mission where we were, trying to, deflect an actual asteroid that was coming at us. So, for instance, on DART, we had a tolerance, kind of a circle around the the center point of the asteroid that we were designing the guidance system to be able to hit within that circle. And for the DART mission, it was really okay for us to hit the asteroid just about anywhere on its surface because again, we just wanted to demonstrate that we could hit it and make a small but measurable change in its orbit. So we deliberately didn't make the requirements too tight on that. But in a real situation, we're coming in at an asteroid, you know, we'll have ideally have reconnoitered that asteroid with another spacecraft beforehand, so we'll know its shape and its size and how it's rotating. And based on its geometry, our our kinetic impactor analysts might say, okay, you really want to make sure you hit this part of the asteroid because if you hit this part, it's less likely that the asteroid is going to break apart. It's more likely to stay together and get and give you the push that you want to get on the asteroid. And so we might have a tighter targeting tolerance for a mission like that than even what we had on DART.
Okay. Um, are there any like specific advancements in spacecraft technology that you think could improve asteroid deflection strategies in the future?
Yeah, that's a good question. One thing that would help a lot would be to continue to improve high power, high efficiency solar electric propulsion systems.
Mhm.
Those systems can deliver a lot of mass to the asteroid to rendezvous with the asteroid, meaning to match the asteroid's speed so you can hang out with the asteroid. And that's very enabling for both nuclear deflection or disruption missions and also for ion beam deflection missions. So that those improvements in propulsion technology are important for those. And then for reconnaissance, for being able to get to the asteroid quickly after a potentially hazardous asteroid has been discovered, we want to improve our technology and our techniques for rapidly deploying spacecraft. So minimizing the time from getting the alert that we need to launch something to getting it to the launch pad. We want to minimize how long it takes us to get to the launch pad so that we can respond quickly in a real emergency.
Okay, is artificial intelligence ever used in planetary defense, or is that not used very often?
We haven't really used it much for planetary defense work as of now, but but AI algorithms are as you know still emerging and are improving at a rapid rate. So we might start to incorporate AI algorithms into planetary defense at some point, but it's a little too early to say.
Okay. Um, yeah, I guess that's pretty much all I have. But to the people that are watching, they wanted to know what advice do you have for students that are interested in pursuing careers in like planetary defense and like space mission design?
So I encourage everybody to do a lot of reading. If you go to nasa.gov/planetary defense, there's a section on our website called supporting documents,
Mhm.
which has a lot of really good reports. Some of them are technical reports, some of them are policy documents. And there's a really good set of documents there. I would highly encourage people to read those. There's a lot of other good resources on that website. The other website I encourage people to check out is the Center for Near Earth Object Studies website. If you Google CNEOS JPL, you'll find the CNEOS website, and there's a lot of good information on that website, a lot of good background information, and pretty easy to understand data about how many asteroids are out there. And there's also a set of simulated asteroid impact scenarios that we've worked through with a lot of documentation and presentation files explaining the analysis procedures. Those are all documented on the impact scenarios section of the CNEOS website. And then finally, the CNEOS website also has a tool on it called the NEO Deflection app or NDA. And
Okay.
it's an interactive online interface that you can use to design your own kinetic impactor missions to simulated threat asteroids. It includes data plots and a lot of technical information that can help you understand how we design those trajectories and things like that. And then the final piece of advice I would have would be to, besides the reading and experimenting with those things, would be to study hard in math and also in computer programming.
Okay.
Those are very important.
Okay, besides like math and computer programming, Are there any like other skills like physics or anything other that's also important for the field?
Yeah, physics is important. But I also recommend, besides physics, learn how to write well. If you can write well, both in narrative form and in terms of making presentation slides, and if you're also good at speaking, if you can get up in front of people and give a good engaging talk about something and effectively communicate the information, engineers get asked to do that more often than you might think.
Okay.